this problem, we are asked to do the error correcting that we learned in the class. So in part 1, first we have to find the polynomial that encodes the message. So the polynomial is going to have, first of all, the polynomial is going to be of degree 2 minus 1 because we have two symbols in our message. So our polynomial is going to be linear. It's going to look like this. P of x equals c1 times x plus c0. And then what we should have is that p of 1 should be equal to 4 and p of 2 should be equal to 2. And this is saying that c1 plus c0 should be 4. And this is saying that 2c1 plus c0 should be 2. Okay, let's go ahead and solve these linear equations. If we subtract the first equation from the second equation, we get c1 is equal to minus 2. And then if we plug back in minus 2 for c1 in one of the equations, we get c0. For example, if we plug it back in this equation, we get that c0 is 6, which is the same thing as 1 minus 1 mod 7. So our polynomial is going to be p of x equals minus 2 times x minus 1. Okay, so the message that we should send is going to be extended by 4 symbols. So we should send p of 1, p of 2 up to p of 6. So let's go ahead and compute these. We already know what p of 1 and p of 2 are. So p of 3 is just 2 times 3, minus 2 times 3 minus 1, which is equal to minus 7, which is 0. Then p of 4 is just minus 2 times 4 minus 1, which is just minus 2, which is just 5. P of 5 is minus 2 times 5 minus 1, which is minus 11, which is just minus 4, which is 3. And then p of 6 is just minus 2 times 6 minus 1, which is minus 13, which is just 1. So the message that we send is going to be 4, 2, 0, 5, 3, and 1. Okay, so let's go ahead to the second part. Okay, so for the second part, we are asked to decode the message that they have received. If you remember, for this you have to set up two polynomials, q of x and e of x, such that q of x is just e of x times p of x, where p of x is the original polynomial that encoded our message, and e of x was the so-called error locating polynomial, which is always defined to be x minus e1 times x minus e2, where e1 and e2 are the two error locations. Now, working with e of x in this form is hard because you would not get linear terms in terms of e1 and e2. For example, you would have the product of the two, which is hard to deal with. So we expand this out and write it out as x squared plus b1x plus b0. And instead of working with e1 and e2 directly, we work with b1 and b2, which are the coefficients of the polynomial. As for q of x, p of x is a polynomial of degree 1, e of x is a polynomial of degree 2, so q of x has to be of degree 3. So we write it out as a 3 x3 plus a2x2 plus a1x plus a0. Now remember, this identity is, well, we defined this, we defined q of x in terms of this identity, but this is itself equal to e of x times r of x, where r of x is the message that we received, which might have errors at some point. The reason why these two are equal is that, first of all, for x's which are not at the error locations, r of x is just the same thing as p of x, so these two are equal. But whenever x is one of the two error locations, e of x is 0, and no matter what we multiply by 0, we get the same thing. So these two are equal, so therefore q of x is equal to e of x times r of x. So this gives us 6 different equations, one for each point, one for each symbol that we received. For example, for x equals 1, we get this linear equation. Q of 1 equals r of 1 times e of 1. I'm just going to write this out, expand this out. Q of 1 is just a0 plus a1 plus a2 plus a3 equals, well, what is r of 1? It's just 5 times e of 1 is just b0 plus b1 plus 1, right? If you expand this out, you get, this is equal to 5b0 plus 5b1 plus 5. Okay, so this is the equation that we get for x equals 1. What about x equals 2? Well, for that one you get a0 plus 2a1 plus 4a2 plus 8a3, and since we're working mod 7, 8 is the same thing as 1, so you get a3 here. This is equal to, well, I'm just gonna write it out. This is equal to this whole thing is equal to 3 times e of 2, so 3 times b0 plus 3 times 2 times b1, which is 6 times b1, and then 3 times 4, which is the same thing as 5 mod 7. So this is the equation that we get for point 2. Just gonna write down the equations for the other points. We get a0 plus 3a1 plus 2a2 plus 6a3 equals 4b0 plus 5b1 plus 1. For the fourth point, we get a0 plus 4a1 plus 2a2 plus a3 equals, this time we have a 0 here, so the right hand side is just 0. For the fifth equation, we have a0 plus 5 times a1 plus 4 times a2 plus 6 times a3. This whole thing is equal to 3 times b0 plus b1 plus 5. And then for the last point, we get a0 plus 6a1 plus a2 plus 6a3. This is equal to 6 times b0 plus b1 plus 6. Okay, so far so good. Now we just have to solve this system of linear equations. Okay, The way we do that is each time we choose a variable, we pick an equation that has that variable. For example, we start with a0, and the first equation has that variable a0 in it. We multiply that equation by something so that the coefficient of a0 becomes 1, and then we subtract appropriate multiples of that equation from the other equations in order to make a0 vanish from them. Okay, so let's do this. I just have to subtract this equation from all of the other equations in order to get equations that do not have a0 in them. So if I do that for this second equation, I'm just going to get a1 plus 3a2 plus, sorry, there is no a3 here. a3 also vanishes. This is equal to 5 times b0 plus b1, and then there is no constant term. Okay, if I do that for the third equation, meaning that if I subtract the first equation from the third equation, I'm going to get 2 times a1 plus a2 plus 5 times a3. This is equal to 6 times b0 plus 3. Okay, let's go ahead and do this for the fourth equation as well. If I do this, I'm going to get 3a1 plus a2 plus, sorry, there is no a3 here again. This is equal to 2 times b0 plus 2 times b1 plus 2. I'm just going to go ahead and do this for the fifth equation as well. For this one, I'm going to get 4 times a1 plus 3 times a2 plus 5 times a3. This is equal to 5 times b0 plus 3 times b1, and then there is no constant term. Okay, for the last equation, what we're going to get is 5 times a1 plus 5 times a3. This is equal to b0 plus 3 times b1 plus 1. Okay, now if you look at this, we have a system of 5 linear equations and 5 variables here. So the way to solve the system of linear equations is to solve this smaller system of linear equations and then plug back in the values we get for a1, a2, a3, b0, b1 into the first equation to get the value for a0. Okay, so we have to continue this exactly what we did here. We're going to pick this time an equation that has a 1 in it. So the second equation has it. And we are just going to first normalize it. There's nothing to be done for normalization because the coefficient of a1 is just 1. Now we have to subtract appropriate multiples of the first equation from the other equations. For example, we have to subtract 2 times this equation from the third equation. And we have to subtract 3 times it from this equation. Okay, let's go ahead and do this. So if we subtract 2 times the second equation from the third equation, what we're going to end up with is going to be this is going to be 2 times a2 plus 5 times a3 is equal to 3 times b0 plus 5 times b1 plus 3. Now if we subtract 3 times the second equation from the fourth equation, what we're gonna get is 6 times a2 plus, well, there is no a3 here, so I'm just gonna write down 6 times a2 is equal to b0 plus 6 times b1 plus 2. Okay. For the fifth equation, if we subtract 4 times the second equation from it, what we're going to get is 5 times a2 plus 5 times a3 is equal to 6 times b0 plus 6 times b1. And finally, for the last equation, if we subtract 5 times the second equation from it, what we're going to get is 6 times a2 plus 5 times a3 is equal to 4 times b0 plus 5 times b1 plus 1. Okay, now we're done with this second equation. So we go to the third equation and the next variable, which is a2. Okay, so the third equation does have a2 in it. We just have to normalize it. So we have to divide by 2, which mod 7 means multiplying by the multiplicative inverse of 2, which is 4. So let's go ahead and multiply this by 4. If we do that, what we're going to get is going to be, well, this 2 disappears. Then the 5 when multiplied by 4 becomes 20, which mod 7 is the same thing as 6. So this is going to become a2 plus 6 times a3 is equal to, well, I'm just going to clear this thing out. The right hand side is going to become 5 times b0 plus 5 times b1. Sorry, 6 times b1. It's going to be 6 times b1 plus 5. Okay, now let's go ahead and subtract the appropriate multiples of this equation from the other equations. We have to subtract 6 times it from the fourth equation. If we do that, what we're going to end up with is this. It's going to be just okay, this is just going to be 6 times a3 equals okay, 6 times a3 equals 6 times b0, and then plus 5 times b1, and then there is no constant term. If we do the same thing with the fifth equation, if we subtract 5 times the third equation from it, what we're going to get is 3 times a3 equals 2 times b0 plus 4 times b1 plus 3. If we do the same thing with the last equation, what we're going to get is 4 times a3 equals 2 times b0 plus 4 times b1 plus 6. Okay, now we're done with this equation. Now we have to go to the next variable in the next equation. So in this equation we have a3. We just have to normalize, which means dividing by 6, which is the same thing as multiplying by the multiplicative inverse of 6, which happens to be itself 6. Okay, so if we do that, this 6 disappears. So we get a3 on this side of the equation. On the other side, we're going to get b0 plus 2b1. Okay. Alright, so far so good. Now we have to subtract 3 times this equation from the fifth equation and 4 times it from the last equation. If we do that, we're going to get, of course, 0 on this side equals. On the other side, what we're going to get is 6 times b0 plus 5 times b1 plus 3. And for the last equation, what we're going to get is 0 on one side, and on the other side we're going to get 5 times b0 plus 3 times b1 plus 6. Okay, now we're done with this equation too. Now let's go ahead and normalize this fifth equation. Our next variable is b0. We want to make its coefficient become 1. So we just have to multiply by 6, divide by 6, which is the same thing as multiplying by 6, mod 7. So if we do that, this 6 disappears. So we're just going to get b0 here. This 5 times b1 becomes 2 times b1. And this 3 becomes 4. Okay. Now we just have to subtract 5 times this equation from this equation. Surprisingly, if we do this, we're going to end up with 0. Okay, so everything vanishes. This is why we have multiple solutions to the system of linear equations. This is because in the last step of the equation, whatever value we choose for b1, we are going to get this equation satisfied. So for every value of b1, we are going to have a set of solutions. Okay. All right. So let's go ahead and create 2 solutions as required by the problem statement. So we're going to have one solution for when b1 is equal to 0. And we are also going to have one solution for when b1 is equal to 1. Okay. Okay, so let's go ahead and back solve this. So when b1 is equal to 0, if you plug it into this equation, you're going to get the value for b0. So this is just saying that b0 plus 4 is 0, right? And that's just saying that b0 is equal to 3. Okay. Now let's go ahead and plug these 2 values into this equation. So this is saying that a3 is equal to 3 plus 2 times b1, which is 0. So a3 is also 3. Okay, what about a2? Well, we have to plug all the values we have into this equation. This is just saying that a2 plus 6 times a3, which is 4, equals 5 times b0, which is 5 times 3, 15, which is the same thing as 1, plus, well, there is no 6 times b1, and then there is a 5. Okay, so this is saying that a2 is just 2. Okay, so let's go ahead and write this down. Okay, now you plug all the values into this equation to get the value for a1. What do we have here? We have a1 plus, what is 3 times a2? It's just 6, equals 5 times b0, which is 5 times 3, which is 1, and then there is no b1. Okay, so this is saying that a1 is equal to 2. Okay, and finally let's go ahead and write down the value for a0. For a0 we are gonna have we have a0 plus a1 is 2 plus a2 is 2 plus a3 is 3. This is equal to 5 times b0, which is 1, plus there is no b1, and then there is a 5. Okay, 2 plus 2 plus 3 is just 7, so this whole thing vanishes. So this is saying that a0 is equal to 6. Okay, all right. So this gives us the two polynomials e of x equals x squared plus there is no b1 and there is b0, so e of x is just x squared plus 3, and then q of x is just, let's go ahead and write it down, it's just a3 times x3, which is 3x3 plus a2 times x2, which is just 2 times x squared, plus a1 times x, which is 2 times x, plus a0, which is just 6. Okay, now let's go ahead and write down the solution for when b1 is equal to 1. So when b1 is equal to 1, plugging it into this equation, we get b0 plus 2 plus 4 equals 0, which is saying that b0 is also 1. Okay. Now what about a3? If we plug in the values we had into this equation, we get a3 equals 1 plus 2 times 1, which is a3 is 3. Okay, what about a2? If we plug in everything we have into this equation, we get a2 plus 6 times a3, which is just 4, equals 5 plus 6 plus 5. So the side is just 16 minus 4, 12, which mod 7 is 5. So this is saying that a2 equals 5. Okay. Now let's go ahead and do a1. Okay, so we have this equation is saying that a1 plus 3 times a2 is just 3 times 5, which is 1, equals 5 plus 1. So this is saying that a1 is also 5. Okay, and then a0 is well, we have a0 plus 5 plus 5 plus 3 equals 5 plus 5 plus 5, right? So these two things disappear with this one, so this is saying that a1 is equal to 5 minus 3, which is 2. Okay, so now this is just saying that e of x equals x squared plus x plus 1, and q of x equals a3x3, which is 3x3, plus a2x2, which is 5x squared, plus a1x, so 5x, plus 2. Okay, so now we have our two sets of solutions. Now we have to divide the polynomials we get by each other. Okay. Alright, so let's go ahead and do this division. For example, for the first one, 3x3 plus 2x squared plus 2x plus 6. Let's go ahead and divide this by x squared plus 3. Okay, for the first term we are going to get 3x here, right? So if you multiply it out, you get 3x cubed plus 3x times 3 is 9x, which is 2x, right? So now if you subtract this out, you get 2x squared plus 6. And then for the next term, we're going to get 2 here. So 2 times x squared plus 6, which when you subtract out, you get 0. So the polynomials were divisible, in fact, and q of x times divided by e of x, which gives us p of x, was just 3x plus 2. Okay. Alright, so far so good. Let's do the other one. So we have 3x cubed plus 5x squared plus 5x plus 2, and we are dividing this out by x squared plus x plus 1. Okay, for the first term we are going to get 3x here, so this becomes 3x cubed plus 3x squared plus 3x, and now if you subtract things out, you get 2x squared plus 2x plus 2. Now for the second term we're going to have a 2 here, so 2x squared plus 2x plus 2. And if you subtract things out, you get 0. So this time q of x was also divisible by e of x, and the result of the division, which gives us p of x, was again 3x plus 2. So the two polynomials we get are the same. In fact, they should be, because that's the message that we sent. Okay, so I'm just gonna clear this part out. Now, what do we know about e of x in the two cases? Well, in order to factorize a polynomial of degree 2, you just have to find its roots. Okay, so let's find out the roots of each e of x in the two solutions that we have. So for x squared plus 3, is 0 a root of it? No, because 0 plus 3 is not 0. Is 1 a root? 1 plus 3 is not 0. Is 2 a root? Yes. So 2 is a root. Why? Because we have e of 2 equals 2 squared plus 3, which is 0, not 7. So from what we know, e of x should be divisible by x minus 2. So let's go ahead and divide it in order to factorize this. So if we divide this out by x minus 2, we get so we have x here, so x squared minus 2x. If we subtract, we get 2x plus 3, and then we are going to have plus 2 here, so we have 2x, and then we have a minus 4, which is the same thing as plus 3, mod 7. Right? Okay, so e of x was just x minus 2 times x plus 2, or I'm just gonna write this out as x minus 5 in order for you to be able to see what the other root is. It's just 5. Okay, so in this case we have two different roots, 2 and 5. Now what about the other e of x? So in the other case, e of x is just x squared plus x plus 1, so let's go ahead and find one of its roots. Is 0 a root? Again, no. 0 plus 0 plus 1 is not 0. Is 1 a root? No. 1 plus 1 plus 1 is not 0. What about 2? Well, 2 is again a root. 2 squared is 4 plus 2, 6, plus 1, 7. which is the same thing as 0 mod 7, so 2 is a root. So again, this thing should be divisible by x minus 2. So let's go ahead and divide. We have x here, so we get x squared minus 2x. When you subtract, you get 3x plus 1. And then we have a 3 here, so you get 3x minus 6, and the minus 6 is just 1. So when you subtract, you get 0, as was expected. So in this case, e of x is just x minus 2 times x plus 3. Again, I'm going to write out the x plus 3 as x minus 4 in order for you to be able to see what the other root is. Okay, so as you can see, both of our e of x's have the same root, which is 2. Okay, this is not a coincidence. If you write out the p of x that we have, 3x plus 2, you will see that it agrees with all of the symbols that we got in all the places. It agrees with this one, 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 it agrees with this one. The only place where 3x plus 2 is not the value that we got is this place, at the point 2, okay? So our error locating polynomial has to be 0 at that point, okay? But the thing is that the number of errors that we had was lower than the number of errors that we could correct, okay? We could correct up to 2 errors, but we had 1 error. So the thing is, our error locating polynomial has to have a root at here, okay? So it has to have a factor of x minus 2 in it, but the rest is arbitrary, okay? Because we don't have any errors anymore. So the rest can be arbitrary, and that's why we have multiple solutions, okay? But no matter what solution you pick, you're going to end up with the same p of x, okay? So that's the moral of the story. They do have a common root too, and that's because there is an error at there. But the rest of the polynomial e of x is completely arbitrary. It can be x minus 4, it can be x minus 5, it can even be x, meaning that it could have a root at 0, which is not one of the points that we send, okay? But it doesn't matter. Another way to look at it is that whenever you have this polynomial e of x, which is x minus 2 times x minus 4, it's kind of like you're saying that there is an error at point 2 and there is also an error at point 4, okay? Well, you could interpret there being error at point 4 as you're changing the value at point 4 to some value, but that value happens to be the same thing that we sent, okay? So you could count a non-error as an error, and that would not ruin your algorithm. Okay,